Now, last class we had a brief discussion about whether or not recombination is good or bad. I just wanted to give you a brief anecdote, a little story about one case in which hitchhiking can be dangerous. Don't pick up the hatchet-wielding hitchhiker. So this example is Crohn's disease. And this was published relatively recently. You'll see the citation for the study in a moment. But if you don't know about Crohn's disease, this summarizes it, I think, pretty nicely without going into great details. It causes bowel disorders. And in the past, using techniques like we've looked at the last couple of days, phenotype mapping, looking at individuals that have this disease and looking at their genotypes, geneticists had discovered that there was a particular part of chromosome 5. So this is just a diagram of chromosome 5. Here, what's that called? The drawing of a chromosome? Ideogram. So it's an ideogram of chromosome 5. There's the centromere. So it's got a P or short arm and a Q or long arm. And what we're looking at here is the genes that are found in the part of the chromosome that's represented by that vertical red bar on the ideogram. So a tiny little slice of chromosome 5 is what we're looking at here. And each of these horizontal lines is a gene. So here we have a bunch of, it's the same gene. And in this case, it's called P4HA2, which doesn't mean anything to any of us. It's just an arbitrary name of a gene. It may be that we don't know what it does, which is why it has kind of a strange sounding gene name. So how many genes are in this region of chromosome 5 where geneticists have decided that Crohn's disease susceptibility is located? We've got like 1, 2, 3, 4, 5, 6, 7, 8, something like 9 or so different genes in this region. So geneticists have narrowed down from the 30,000 or so genes we have in our genomes to this little chunk of chromosome 5. And one of these genes supposedly contains a mutation that causes, or at least increases susceptibility to, if not causes, Crohn's disease. So the question is, first question, which gene? These are some of the players. We've got, and don't go to Socrative yet to do this. I'm going to finish the entry quiz first, but just for a second, you don't know anything about these genes necessarily, but I want to take a quick poll from you. Which of those 3 genes do you think is more likely to cause Crohn's disease? OCTN1, which is a dietary antioxidant transporter, or IRF, the interferon regulatory factor, or interleukin, IL-5. So for those of you that are still working on the quiz, you better finish now, because I'm going to turn that off and I'm going to actually keep working. Let's do a show of hands. We don't need to use technology all the time, right? Who thinks that OCTN1 is the most likely candidate for causing an gastrointestinal disease? 1, 2, 3, 4, 5. Okay, what about IRF, interferon regulatory factors? What's interferon? You're right, it's an immune system related protein. Okay, what about interleukin? Okay, so 5 of you have a guess. Let's try this again. Who thinks that OCTN1 is the most likely cause of Crohn's disease? Okay, about half the class. Okay, how about IRF? 1. Interleukin. Okay, some of you are still not playing, but that's okay. So the vast majority of you think it's OCTN1, dietary antioxidant transporter. So it turns out that there are mutations in OCTN1, but this mutation that these scientists discovered is a beneficial mutation, right? Not all mutations are bad. Mutations don't just cause Teenage Mutant Ninja Turtles. Sometimes they are beneficial to us. They improve something. And in this case, there's a specific mutation in that gene that causes your gut the ability to take up more antioxidants. If you watch those Palm Wonderful commercials and they've got the antioxidant fighting ninjas that come in with their swords and start killing the antioxidants, right? That's supposedly good for us. If your intestine can take up more antioxidants and fight the free radicals. So a beneficial mutation. What Huff et al. In 2011, this citation down here in the bottom right of the screen, wound up doing was they knew that the gene or the mutation that causes Crohn's disease was in one of these relatively small number of genes. And they had a hypothesis. And in this case, their hypothesis was that if you take a bunch of people that have Crohn's disease and you look at the gene expression, which means protein production, how much in each of these individuals that have this disease, how much protein is produced from each of these genes? Are they turned on or are they turned off, essentially? And they wanted to know if there's a correlation between if you have Crohn's disease and the amount of gene expression, the amount of protein that's produced from each of these genes. So here on the left, for example, is P4HA2, whatever gene that is. Is there a difference when you look at these two graphs right here? Here's the graph data, gene expression on the y-axis, relative gene expression. Data from people with Crohn's disease, people without Crohn's disease, the controls. Is there a difference? Slightly. What these are, by the way, if you have never seen a box plot before, it's just a way to represent data. Each of those individual data points is gene expression measured from an individual, like right there. That's one data point from one individual. The box plots summarize the data. That middle line is the average of all of the data points. The top of the box is the 75th percentile, and the bottom of the box is the 25th percentile. So it gives you an idea about the spread of the data points. So in essence, these two data sets are not different. So it doesn't matter if you were a person I picked at random who has Crohn's disease or not, your protein expression, your protein production from your P4HA2 gene I wouldn't be able to distinguish who's got the disease and who doesn't. So which of these genes can you do that with when you compare a Crohn and control column? So IRF1 looks like there's a big difference between if you've got Crohn's disease, you make a lot more of this protein than you do if you're an unaffected individual. So, punchline, IRF1 is the gene where there's a mutation that causes susceptibility to Crohn's disease. And this is how the scientists ruled out from those 8 genes that was the one that had a statistically significant difference between if you have Crohn's disease, you make more of this protein. If you don't have the disease, you don't make as much of the protein. Now here's a case, unlike the Dalmatians, where we know something about the genetic basis of the disease. The question is, why do so many people in society have Crohn's disease? It's pretty common. So why do so many people have this mutation? Are they more likely to have more kids or something like that?
Are you saying it's more common now?
Just in general, it's like brachydactyly. Well, not really. Brachydactyly is pretty rare. Crohn's disease is a pretty common disorder. Like a lot of people have it, not just since they discovered the genetic basis, but in general, a lot of people suffer from Crohn's disease. If it's a disease, shouldn't it be, as was suggested earlier, eradicated naturally from the population?
It's not deadly, so it's not killing off people, and then it's not something you can see, so it's not going to affect people like finding a partner.
Okay, very good. So we're moving a little bit into evolution. So we're talking about if this mutation doesn't kill you and you're still able to have kids, you can pass this mutation on to your offspring. And unless Crohn's disease makes you super flatulent and you're not able to find a mate because it's socially awkward, then yeah, you're likely to be able to pass this mutation on to your kids. It doesn't do anything like make you sterile where you can't have kids or kill you early before you're able to have kids. I just want to run you quickly through a model of how scientists and geneticists in particular think that the Crohn's disease mutation exists so widely in the population. So there are 2 mutations now we've talked about so far. There's the one in IRF that looks like it causes susceptibility to Crohn's disease. And then there's this mutation I talked about earlier in this gene called OCTN1, which is the mutation that allows your gut to take up more nutrients. more antioxidants. Look at where they're located. What sort of genetic terminology have we used recently that we would use to describe those two mutations, those two alleles? They're linked. They're on the same piece of DNA. If you inherit one, you inherit the other. So they travel together. If you get the mutation that causes Crohn's disease, you also get the mutation that increases dietary antioxidant absorption. So what does that have to do with the prevalence of these mutations in the population? Now we have to think about the whole human population level.
Could it be that they counteract each other, and there's a possibility that crossing over would lead to something?
So low possibility of crossing over because these genes are linked, but you're on the right track with the counteract each other, although not directly counteract.
Is it epistasis, like monastialism?
So it's not epistasis. These genes, the gene products, the proteins don't actually directly interact with each other, but it's similar concept.
Okay, I wanted to ask you a couple things, like, first of all, is that limited here to the population of the United States or is it worldwide?
I don't know offhand, but I think the idea is it's worldwide, if I remember correctly.
Okay, because I was gonna comment that if it was, like, specifically here in the United States, it was more of an environmental factor would play.
Sure.
Like,
Yeah.
Like you said, we have an antioxidant-rich food source now, and I'm wondering if that's actually triggering the IRF to also become active.
In this case, no, but that is a reasonable hypothesis that you might expect these mutations to exist only in small parts of human populations.
I have a question. For the IRF, is that saying we're increasing the amount of interferon in this like that's being exhibited, or is it decreasing the amount of interferon being exhibited?
Well, it looked like the protein production went up, so maybe that's somehow detrimental to gut function.
Is that protein to like inhibit interferon production, or is that directly related?
Don't remember how interferon regulatory factor 1 is what IRF1 stands for, but I don't remember which direction it regulates interferon. Something that's worth looking up potentially. So these two mutations are linked. They travel together. They don't counteract each other. These two genes, their two proteins that they produce, do not directly interact with each other. But they travel together. So the fact that they still exist in our society, that they haven't been eliminated by natural selection, means something.
The centimorgans are really small.
Well, it's true, they are very close to each other, so there are a very small genetic distance between them. What's happened, one mutation is beneficial, one mutation is detrimental. So think about the human population many generations ago. Here are 5 different chromosomes from 5 different individuals. I'm just going to try to model the human population with 5 different individuals. Which is the best chromosome you could have on this slide? If you number them from the top 1 through 5. Which is the best chromosome? Which one would you pick if you were genetically engineering yourself? 3? Or 4 or 5?
Yeah, 3,
Why?
4, 5. Because they don't have the detrimental.
They don't have the detrimental allele. But why didn't you pick chromosome 1?
Because it has both, you don't know which one.
I would have.
Go ahead.
Wouldn't 3, 4, and 5 have a higher chance of being crossed over to get the detrimental?
Not necessarily have a higher chance of crossing over leading to the detrimental mutation. So consider this. These 2 mutations, we're going to see this in the next slide. These 2 mutations are so close together, crossing over almost never happens between them. They are almost perfectly linked. Recombination almost never separates them. So if you get one, you get the other. So obviously you don't want chromosome 2, right? It's got a bad mutation on it, so no one's picked chromosome 2. Chromosome 1 is the chromosome that a lot of people in our population have. So why do most of our population, actually, this is kind of what our human population looks like now. Most individuals either have the chromosome that has no mutations or they have the chromosome that have 2 mutations. What does this tell us about the benefit versus the detriment?
Benefits outweigh.
The benefit in this case, the theory is that there's a net benefit. That when you compare both of them, it's more beneficial for most people to have that dietary antioxidant transporter mutation that's good. And there's maybe a slight decrease in your overall health or fitness by having the bad mutation. So there's a net benefit. And when there's a net benefit, what's going to happen when you have this chromosome, these chromosomes, those are plus, beneficial. If you don't have either of those mutations, that's kind of neutral. Not good or bad, it's status quo. It's just the way things used to be. So the number of people in our population that have the bad mutation is increasing because having both of those mutations is, on average, better for you in general. And that's the hypothesis here, that Crohn's disease, yeah, it's a disease, but it comes with a benefit at the same time. It's not one that most people understand or are aware of, but if you get Crohn's disease, then apparently you've got more antioxidants that you can use. Any follow-up thoughts or questions about that? So that's an example of linkage, and how linkage and absence of crossing over, complete linkage between two mutations, can affect human health. So sometimes it's bad to have mutations that are perfectly linked with some good, some bad. You can never separate the two by recombination. Something like, I skipped past that slide already, but let me just give you the statistics since, bless you, since I calculated earlier, some tiny fraction, about 1 in 181 crossover events on chromosome 5 will lead to recombination between those two genes. That's how close together they are on the chromosome. So it's really, really rare for recombination to separate those two mutations. If that happened, what would happen to the human population, to this chromosome? If you could have crossing over happen, then you could separate the beneficial and the detrimental mutations and generate chromosomes that only have the beneficial mutation. That just hasn't happened yet, apparently. It's really rare.
Because you were saying that the octanol, you have a better ability to maintain antioxidants.
Right.
So you could
Absorb them from your diet.
just-
Yeah.
so this would be more, so this would be evolutionary, that if having the interferon 1 present with octanol most often, you'd rather have, and what are, let me back up, this is my other question.
Yeah.
Could this be more common because we have diets that allow for more antioxidants within our diet compared to what would have been longer ago?
Fair enough. So yeah, the question is there a net benefit to this combination of mutations because we have so many available antioxidants that we can uptake? For example, in other words, if you were living in a situation where your diet did not contain any antioxidants in the first place, would there be a net benefit of these chromosomes? If your body has the ability to take up antioxidants at higher efficiency, that's good, right? But what if there are no antioxidants in your diet? Then who cares what your gut's going to do? So then you might be in an environment where this combination is actually a net detriment, not useful to you. So a valid point.
Is there a correlation between antioxidants and Crohn's disease?
Not that I know of. But something that's worth looking into. It'd be interesting to know, for example, why these two genes are on the same chromosome for the first place. They could equally likely be on separate chromosomes.
For the gene that causes the Crohn's disease, now that we know that this is a specific gene that causes the Crohn's disease, is there a way where we can just, like, maybe cut that specific gene out so that the next offspring don't?
So what do we want to do now that we potentially have a target for fixing people that have Crohn's disease? Oh man, tricky. What's one problem potentially with removing the gene that causes Crohn's disease?
You don't know what else
Yeah, so what does this gene normally do, IRF1? Because if you take it out because it's causing a disease, that's okay, unless presumably that gene does something beneficial for us because we have it in our genomes. The mutant version is doing something that's not useful for us, but I'm going to move on, sorry folks, but I'll answer questions after the fact if I can. So that's genetic hitchhiking. When you have one bad mutation that hitchhikes, it goes along with, from individual to individual, a beneficial mutation. Beneficial mutation is being selected for, and these sort of weak, bad alleles or mutations get dragged along with them on the chromosome. I want to get to something where you get to do some work now, not me just tell you stories about genetics, although I enjoy telling that story. Last time we looked at one sort of phenotype mapping, and I was looking at correlations between the genotypes of individuals and the phenotypes. And in last class, that example was, what were we talking about? So this was hairy leaves. Last class, I introduced this concept looking at a different phenotype. We had genotypes of individuals and we had a phenotype, some sort of trait. And we figured out that there was a specific gene that caused, skin color or hair color or something like that. So this is a slightly more complicated version. It's called complex trait mapping because this is what's going to happen if there's a situation where 2 or more genes control the trait you're trying to study. So here's the setup. Again, I introduced this at the end of last class. What gene controls the hairy leaf trait? Did you find a part of the chromosome, blue versus red allele, that causes hairy leaves versus not? All right, let's take the pulse of where we're at. What are the recombinant haplotypes? The P0s. What's the parental type? AB? So we've got capital A, capital B as a parental type, and lowercase a, lowercase b. We get that from the genotypes of the P0s. So what's the genetic distance? Which of phenotypes or genotypes 1, 2, and 3, and 4, which of those are the recombinant types? 3 and 4 with the big A with the little b, the little a with the big B. recombinants. So 12 plus 13 divided by 51, the total number of observations, gives us recombination fraction of, what is it? 0.49. Okay, so that's the AB genetic distance. What's the answer to the second question?
Unlikely.
Possibly.
Unlikely.
Possibly, unlikely. What about, so what's our rule?
50 or
If it's less than 50 centimorgans means genes are either at the ends of one chromosome or they're on separate chromosomes. If it's less than that, we would conclude that they are linked. Except you're all right, those of you that said, well, maybe or possibly, or why are you right?
they're so far apart about recombination continuum still
So 0.49 is pretty close to 0.5. So how sure are you that these genes are linked? 0.49, 0.5? You willing to bet some money on whether or not they're on the same chromosome? Sir?
The way it was, I read that back for past examples, and if that number 3, if one more child is, even if one more that's already pretty close, that would put it exactly 50.
Exactly right. I hope you heard what he just said, because that's exactly the point. And if you didn't, then I'll restate it. This is the big what if. So yes, these genes look like they're linked. We calculated a genetic distance of less than 0.5. But he said, what if we happened to collect one more individual, one more F2 offspring, and look at it, and it had genotype number 3? By chance. We just haven't sampled enough offspring yet. What would happen to the genetic distance if there were 13 genotype 3s? Now what's the genetic distance? Now it's 0.5. Now we don't know if the genes are linked or not. So the real question is, how certain are you in your calculation of genetic distance? When you, yeah, absolutely, you can calculate 0.49, but you have to have a lot of observations to support the idea, the conclusion that that actually means that the genes are on the same chromosome just really far apart. So what do we do to statistically address this point? This is where we use the chi-square test. We want to know how certain are we that 0.49 really is 0.49 and not actually 0.5. So how would we set up the chi-square test for this? Bless you. So we've got observed values. That's the column on the left there, 13 big A, big B haplotypes and so forth. For any dihybrid test cross, what's the expected ratio of those four? There should be an equal number, 1 to 1 to 1 to 1, of each of those four genotypes. So how many expected? We observed 13, 13, 12, and 13. What are expected values? It's the Punnett square from that F1 dihybrid test cross. The tester has one haplotype, and the dihybrid produces 4. The 2 parental types and the 2 recombinant types. So there's an equal frequency, 1 to 1 to 1 to 1 ratio. 25% of, we expect 25% of those 4 genotypes.
You expect about 13 of each?
Well, it's not quite, because the total, yeah, what is it?
75, 12.75.
It's 51 divided by 4. Okay, so we should have observed if the genes are truly, what's the expectation based on? Genes are on separate chromosomes, independent assortment. That's always the hypothesis for genetic distance. Mendel's true. Mendel's right, independent assortment. So we should have seen we expect to see, if the genes are truly unlinked, 12.75 of each of those 4 types. So then you can set up the chi-square test. I urge you to do this after class, Google Sheets, or not, use your calculator, observed minus expected squared over expected for each of those 4 different pairs of observed and expected values. Add them all up. In this case, the original one, in black ink, the chi-square value, when we calculated a recombination fraction of 0.49, you should get, when you do that calculation, a chi-square value of 0.058. So while we're in class together, I want to walk you through that chi-square table one more time to interpret this p-value before we go. So what 2 things do we need to figure out a p-value? I just gave you the chi-square value. We need to know degrees of freedom. How many degrees of freedom are there in this example? We have number of categories minus 1. So we've got 4. Why are there 4 categories? 4 different genotypes. We've got 4 different genotypes. Each of them is a type or a class that we're tallying here. We've got 13 of one type or one category. We've got 13 of another category and so forth. So the number of degrees of freedom, 4 minus 1 is 3. So if I load up our chi-square table, we've got degrees of freedom is 3, so we want to look in that line. And what was that chi-square value I said? 0.0 something, which is enough information. We find out where that number is. It's in here somewhere to the left of 0.11, between 0 and 0.11. We look up here in the top to find the p-value, which is greater than 0.99. It's basically a p-value of 1. What does that mean? The p is greater than 0.05. We can't reject the null. So the probability is, in this case, greater than 99% that our null hypothesis is true. 99% plus chance that the null hypothesis, which is that the genes are on separate chromosomes, is true. In other words, even though we calculated a genetic distance that's less than 0.5, there is not sufficient evidence to call these genes linked. Yes?
I understand how you're at in the 3 column, but why do you use 0.99?
You find where that chi-square value, that I calculated, you haven't yet, but again, please do so on Google Sheets or Excel or by hand. When you find that chi-square value, you look in the degrees of freedom row and you find where that chi-square test statistic value is located. So 0.05 is somewhere, it's not between 0.11 and 0.58. It's between 0, which is where this starts, so it's not shown, and 0.11. So our chi-square value lies somewhere in there. And that's why we look up in the top, and that's the p-value that's associated with that chi-square value.
There's some patterns that we can start to see.
Okay, hang on to that thought. Yeah.
I'm confused on how we know which is our null hypothesis.
Null hypothesis is always based on Mendel's laws.
So it's always gonna be
We always assume for genetic mapping, we always assume genes are unlinked,
genes are unlinked.
separate chromosomes. So the Punnett square is always going to be where we get our null hypothesis. Our expectation. Yeah, Punnett squares always give us our null hypothesis. I'm going to skip over this last review. for a second, but I want to present you with the things I'd love to have you look at for next class. And by the way, there's a Socratic, not a quiz, but I'd love to have you answer it. It's open right now if you want to start working on it. It's just a couple of questions. I'm trying to figure out if I need to change one of my office hours to fit the schedules of those of you that have something after class on Mondays and Tuesdays. So please answer those questions. I'll decide whether or not I need to move either the Monday or the Wednesday office hour, maybe to the hour before class. But in the meanwhile, I just want you to take a look at a couple of pedigrees. We're going to be starting to talk about pedigrees next week. And take a stab at answering this question. Here's a huge pedigree. After you watch the video for next class, try this question. See how you do. So that's one thing to do for next class. The second thing is the last slide in this deck of slides that we've got in front of you has the video to watch. Don't watch the whole video, it's a long video. Just watch the first 10 minutes or so. That's the material for Monday. I'll ask you to watch later parts of it for later classes. And finally, do that last bullet point on the last slide. So you can use any sort of tool you want, but draw me a pedigree and turn it into the Google Classroom exercise I'm about to open. You can draw it in any program you want. There's a cool website that lets you draw really nice looking pedigrees that I've provided a URL for. But you don't have to use that tool. You can if you want to. So 3 things for next class. Try that pedigree analysis, draw me a pedigree and send it to me from Google Classroom, and then watch part of the video. We're going to get into pedigrees. All right. Hope you all have fantastic weekends. Come up if you've got a question. I can hang out for about 5 minutes and answer questions.